Hi gents, welcome back. This is our next video in the relative velocity. Apologies for taking so long to get back to you with a new video. I was in the middle of sixth year mocks, as you can imagine. That had a big priority, but anyway, they are out of the way, so hopefully we can get through this stuff now a little bit faster. What we did the last day was we were doing these particles at awkward angles to each other and their relative velocity. And I gave an example, and I asked you to do one, two. We did one, I think, and I asked you to do 2 and 3. So hopefully you found that okay. Thank you for nobody giving me any feedback whatsoever. But since I didn't hear any complaints, I'll assume that all is well. What we'll do today is we'll have a look at actually the most difficult one inside there. So that's question 8. It's on page 56 and it's 4C. So again, these are things which are at awkward angles to each other. So let's kick straight into it. We use this as our example for all the tougher ones that are in it and go from there. Okay, so first of all, let's see. Yeah, our pen is working fine. What we'll do is we'll just draw this thing out and I'll have a look at it. It says 2 straight roads intersect at a point O and cross at an angle 60 degrees to one another. On one road, car A is traveling towards O with uniform speed 16 meters per second, and on the other, car B is moving away from O with uniform speed 20 meters per second, and they provide a diagram. So we'll do that very roughly. So what do we have? We have B, which is here, and it's currently 200 meters away. And we have A, and A is actually traveling in this direction, where B is going away from O, which is right here. We're told there's a 60-degree angle between the two things there, and its gap, not to scale, A currently is 450 meters, beg your pardon, away from O. Okay, what are we told? We're told that A is traveling at 16 meters per second, as it is towards it, and B is traveling at 20 meters per second away from O. Okay, so that's what we have so far. We're asked to calculate the velocity of A relative to B in this sense. Okay. So let's just go ahead. Let's just go ahead and do that. So I think the thing we need to talk about here, velocity of B is very easy to get. Maybe do that one first. The velocity of B, it's obviously moving to the right, so it's 20I, no J's, not going up or down. So that bit's fine. A is a little bit more tricky, so we'll just have a little look at what A is doing. And maybe if we just put A here for the moment, remember that down here was 60. So A, which is there at the moment, if we call that O, if I just draw a line which is parallel to it, we know that that would be 60 degrees because of alternate angles. Okay, so we know that that is what A is doing at the moment. And if we just maybe draw in a right angle here, we can now resolve what it's doing. We know that it is going 16 meters per second along here. So we know that that's 60, and we know that there's 60 degrees. So if we call this X, and we call that Y, what can we say? We can say that the cos of X, sorry, we can't say that. We say the cos of 60, I beg your pardon, is equal to X over 16. So X is 16 cos 60. And similarly, sine of 60 is equal to opposite over hypotenuse, which is 16. So Y is 16 sine 60. That stuff we should know already, but you know what? It might not be a bad idea just to do a little refresh. It has been a while. So let's see, cos of 60, that's very handy. That's a half. So we have that X is 8. And Y, let's put in sine of 60 into the calculator. We have root 3 over 2, so that's going to be 8 root 3. That's what Y is. So look, if we're putting that all together, we have that the velocity of A is equal to. So how many i's? Well, remember, it's moving over to the left. So we know that it's moving over 8. This is per second, of course. So because it's left, it's going to be 8i, minus 8i, sure, sorry. So minus 8i, and we also know that it's going down, and it's going down by 8 root 3. So minus 8 root 3j. So there we go. That is what that's what A is. Velocity of A is, and you can of course get that by just doing u cos theta I plus u sine theta j. But just a little reminder of where those things are coming from. I'm just going to get rid of those calculations. So if you do need to take it down, maybe pause here and go do that. But we'll clear them off here. So the first question. Easy enough question just to start it off, but an important one nevertheless is calculate the velocity of A relative to B. So velocity of A relative to B. So just a reminder, that's velocity of A minus velocity of B. Okay, so that's A just stays the same and we take away B, so that's only going to have an effect on the i's, so minus 28 i's minus 8 root 3 j's. Okay, so that's where we're at the moment. Number 1, nicely done. Okay, you'll remember maybe from the last time that the plan is to allow things to develop, and as you develop them, what you're going to be able to do is you're then going to be able to have it so that A is going to be in line with B. So you want it to be perfectly in line with B. So let's allow the situation to develop, and we will allow A to progress along the line. How it'll be in line with B when it reaches O. So we just got to see how much time is that going to take. So we get out our little triangle. Okay, so the time taken in that instance is going to be distance, which is 450, over speed, which is 16. So just see if that's in any way a nice number. I suspect it isn't. It's not especially. 225 over 8. Okay, that's how many seconds it is. So what we're allowing is we're allowing A to get all the way to O. And of course, in that time, B is going to be traveling, and it's going to be traveling at 20 meters per second. How long is it going to do that? Well, it's going to do for that many seconds. So we need to know where is B inside all of this thing here. Okay, so obviously what we will do is we will take our distance is speed by time. So the speed is 20 meters per second, and the number of seconds is 225 over 8. So let's multiply that by 20, and we end up with, don't know whether to leave it as a, I think we'll just write it as a decimal because it's not too bad. Okay, so it's that many meters, but just remember that's the distance that it's traveled in that time, and it was already 200 meters away from O. To begin with before this time passed. So let's just make a new diagram. We're letting 225 over 8 seconds pass. And what does our new diagram look like? Well, what has happened is that A has got all the way there to O. So there's A or O, I suppose. We'll do it like that, and B is over here. Okay. B is over there. So this is where we're at. What is that gap? Well, B has, sorry, I should say, is this B? I think it is. Yeah. B has traveled 562.5, and it was already 200 meters along the way. So we now know that our gap is 762.5 meters. Okay. Now what we do is we hold it in position, and we're now going to have a look at what is the velocity of A relative to B. Okay, so B stays in position, and we have that it is A now moving, okay, as seen from B's perspective. Okay, as seen from B's perspective. And what we know is that from this moment, what it's going to look like as far as B is concerned is that every second that passes, it looks that A is going to be moving over to the left 28, that's in minus 28i, and it's going to be going down minus 8 root 3j. Okay, so that's what it's going to look like. And so we actually draw that in. So it's moving over 28 and it's going down minus 8, going down 8 root 3i's. So it's doing something like that. Okay, what's this thing here? This is going to be 28 right there. This is going to be 8 root 3. Okay, obviously it's moving over to the left, but I'm just saying that's what it looks like. Okay. Now let's actually answer read the question first of all. If at a given instant A is 450 meters from O and B is that, calculate the time intervals until the cars are nearest to each other. Okay, so A basically is going along this track along there. Okay, it's going along there, obviously on the main line itself, and we want it to be as close to B as possible. Now remember, B is still in all of this because it's the velocity of A relative to B. So what I'm going to do is I'm just going to give myself a little bit more space up above here. And of course, in order, I'll just continue that line on. In order to be as close to B as possible, it needs to be at right angles. Okay, that is the moment when it is as close as possible to it. Okay. How are we going to get that particular distance that it has to travel back in time to? So what we're actually interested in, it's not asking us what is the distance itself, which will be that particular value there that we go and look at. It's asking us the time at which they're going to be nearest to each other. So we actually need to find out, this distance here. Okay, that's from there to there. So that's what X is. And might be a good idea maybe just to pause the video, have a little bit of a guess here as to how you might go about it. Okay, you do actually have enough information here in order to do it. So have a little pause of it, tease it out, see if you can manage it, and I'll tell you when you're back. So okay, let's see if you're able to figure it out. So I had actually given you a bit of a hint with the 28 and the 8 root 3. It's handy to have that there because we are going to know what this angle is here. Maybe not what the angle is, but we can say quite a bit about it because that angle and this angle are the same as each other. So in terms of that first theta on the left that I've written, we have the opposite, we have the adjacent. So it turns out that tan theta is equal to 8 root 3. It's the opposite. This is of course a right angle over 28. Okay, and when it comes to our other one, what do we have? We have we're looking for cos theta really. So we have the cos theta is equal to X over 762.5. Okay, so it's going to be helpful here to find out what theta is. There's a few ways to go about it. Let's see. I'm always a fan whenever you have that of just doing a little bit of Pythagoras' theorem and going from there. But anyway, we know that it's going to be 762.5 times the cos of theta equaling to X, which is going to help us get the answer that we want. So I think this is what I would do. I'm more, of course you can go and get theta is equal to tan inverse and chuck it in there, but I'm always a fan, if you have tan theta and you want to get cos theta, I always like to draw a right angle triangle. So good idea to do this, I think. We have theta, tan is opposite over adjacent. So we know that that's 8 root 3. The adjacent is 28, and we just want to get the hypotenuse. So h squared is equal to 28 squared plus 8 root 3 squared. So I'll just type that into the calculator. 28 squared plus, don't forget a bracket around the 8 root 3. That has caught quite a few of my sixth years out to their shame in the mocks. So you want to watch out for that. And h is going to be the square root of that answer. So h is equal to 4 root 61. Okay, that's what we have. Now, how is that helpful? It's helpful because we can say what cos theta is. Cos theta is equal to 28, the adjacent over the hypotenuse, which is 4 root 61. So there we have it, 762.5 times 28 over 4 root 61s. And that is what x is. So let's do that. Okay, multiply by 762.5. Okay, that doesn't come out as a particularly nice number for me. It just says x is equal to 683.3968,466. Okay, so this is what our distance is as we have a little look. God, you have to turn your phone sound off everywhere in that case. So that's I think not I think that is that particular distance there. Now, remember, when has this thing actually occurred? What we allowed was from our initial position, we allowed A to reach the position so that it was level with B. Okay, but what we're finding out is that actually the closest approach to each other was back in time. Okay, it was further back. It occurs at this particular thing here. Okay, so what we want to say here is we want to go and find out, this is all about timing. We want to find out when that particular thing happened. Okay, so let's just write down a relevant formula, and that is that the time, so it's like the one above, it's equal to the relative distance divided by the relative speed. We're just after getting the relative distance. The relative distance is 683 point whatever. Okay, now the question is, what is the relative speed? So that's an important question to ask yourself. And this is just, the relative speed is simply what is the velocity of AB, but it's what's the magnitude of that particular thing there. Okay, it's the magnitude of it. So we know that it is the square root of, and in fact I suppose we may as well write it down in here while we're at it. We don't even need it there. What's it moving? It's moving over 28 and it's moving down 8 root 3s. Now it's up to you. You can put in the minuses, but of course they're just going to be squared anyway, so it's up to you if you want to do that. Squared plus 8 root 3 squared. Okay, this is the time, of course, and really what we're doing is we're going back this particular time here in order to be back where the nearest pass occurs. Okay, so we got to type out this awful thing into our calculator. So we'll press divided by, and you'll have to give me a second now to type this all in. So, root of 28 squared added to, again in brackets, 8 root 3 in a bracket squared. Okay, and actually, funny enough, that comes out as precisely a nice number. It's 175 over 8, and that's seconds. Now, if you think about it, from our initial time point, what do? We let A roll on so that it was in line with B, and that took 225 over 8 seconds. And what we've just found out is that the closest approach happened 175 over 8 seconds before that. So from the initial time at which they set off, okay, it takes that in order for it to be in line, and then we have to go back 175 over 8 seconds. So that to me looks like 50 over 8 seconds from the initial time period. Okay, so that is allowing for when A when A is setting off. Okay, and I suppose we'll call that 6.25 seconds. So there we go. That is no doubt that's no doubt a tricky question. Okay, what's the tactic behind it? Just as a little review, what you want to do is you want to let A move off so that it's in line. Okay, and this gives you then all of this information up here, and you can actually use that to get what is that particular distance where you would be at right angles to B, that is to say at the nearest approach to B. And from that you can work out that the time you would need to go back. So we have gone back that time from our initial condition. Okay, that's the answer then to part 2. We'll have a look at the final part. I think there's one final part. Yeah, sorry, well actually they call that B part 1. So we'll do that as well. So there's the answer to B part 1. B part 2 says, when are they, okay, calculate the time interval until the cars are equidistant from O. Okay, you actually have to go back up to our initial thing here. Okay, well, maybe we'll do it in this portion of the screen here. Okay, we want them so that they're equally distant from O. Okay, if we just have a little look at A and we'll say, what is the distance from A to O? Well, at the moment it's 450 meters. But in 1 second's time, obviously it'll be 16 meters closer to it. So what we can say is that the distance from A to O, it's 450, but every second, every t, it's going to be 16 meters closer. So that's what you can say the distance between A and O is. I think that's a nice way to think about it. And of course, the same is true for B. B is currently 200 meters away from it. But every single time you leave a second, it'll get 20 meters closer. So its distance is 200 minus 20t. So what do we want? We just want their distances to be the same. So after all of that, actually something which is not too bad. Although I'd say you could tie yourself up in knots thinking about it in that case. So what do we have? We have this thing here. Does that make sense? Actually, it doesn't make sense. Let me just have a quick little think. What have I done wrong? Oh, of course. B is going away from O. So it is not that it's 20 meters closer every second, it's that it's 20 meters further away. It's always nice if you get that time is not working out. It gives you a little hint that you overlooked something. So there we go. We can just say that that is the case. So it's 20 meters for every second. And now this makes a lot more sense. And we get 36t. So t is equal to 250 over 36. That's how many seconds it's going to take. That might just be the nicest way to write it. Yeah, it's just going to be as a fraction. So 125 over 18 seconds. Okay, that is that's the time that has to pass before they are the same distance from O. Okay, look, that's that one. It's the toughest example that they have, and it is a tough question for sure. So here's what I'm going to set for you. If you guys can try page 56, same topic, obviously same sort of questions, and these ones I'd say they're pretty much as tough. They look it anyway. I'm going to ask you to do question 6 and question 7. Okay, see that question 7 is very similar in that it starts off with the same angle as it goes along. So if you guys can do 6 and 7 for me. If you have problems with it, please email me. Let me know, particularly if you want me to give out the answers to 6 and 7. Obviously you have the answers in the back, but if you want to see the workings out of them, just email me. You have my email. So please do use it. Okay, gents, take care, and talk to you soon. Okay.